My name is Eskil Steenberg, and this is a presentation on HxA. HxA is a convention for graphics. So what does that mean? Well, let's start with a simple problem. We're trying to draw a teapot. It's a simple thing that lots of people have done. It shouldn't be hard, right? So why would anybody want to do that? Maybe you're a student trying to learn to do graphics. You're doing your first rendering. Maybe you're learning DirectX or Vulkan or OpenGL. Maybe you're a game developer that wants to build a custom engine and you want to load in an asset. Maybe you're a researcher doing geometry processing or something like that. Maybe you're writing your own ray tracer. Maybe you're a tool maker that needs to import and export assets into your tools. Maybe you're a technical director at a visual effects house or something like that and want to build a simple little tool for doing something in your pipeline. And maybe you're using a weird language like C or, any other kind of language that isn't commonly used. So what are the problems? Well, you need a format, right? How do you load the file? And there's a bunch of formats out there. You can use Alembic. The problem is that Alembic is not specified. You can't read the spec, and it's only a dependency, which means you have to download a big package. You have to make it run on your platform. You may not have bindings for your particular language, and so on and so forth. You can use FBX. FBX is used everywhere, but again, it's a dependency. It's a library. It's not specified. It's not an open format, and the only bindings are for C++. USD is also only an implementation. You can't implement it yourself. You can, but it's really large. And USD is not really for assets. It's more about scenes and compositions. And in fact, it is a pretty good companion to what HxA does. Collada is a huge format, takes forever to implement. It is XML, which, is kind of old, and it's really only for delivery, meaning that it's not for moving geometry and graphics from one application to another. It's moving it from the tools where you make it to the final destination. Another problem is that it's a dead format that nobody supports anymore. GLTF is alive, but it is also huge. It's JSON, which means it's a text format. You have to parse text, and it's also a delivery format. So it does a bunch of things with your data that you may not like. Then there's OBJ, which is an ancient format. It's also text, but at least it's actually implementable. It's actually useful. And that's why OBJ stays around, even though it kind of shouldn't, because it's not very good. So the question is, how do I load a file if I want to write a loader in an hour or something like that? Well, you can't. And the same goes for bitmaps. It's not just geometry. You can load an image. Most images are in JPEG or PNG, and those are difficult formats. You can definitely not write one of those in an hour. There are some really good formats like TGA, which you can implement, in 20 minutes. It's super easy. They do have some sort of non-trivial things, like there's optional compression, but you can turn that off if you really just want to load pixels. But beyond that, you run into a bunch of problems, because if you work in graphics and GPUs, you need one-dimensional textures, three-dimensional textures, cube textures. You need, number of channels that are not just RGB. You need RGB alpha, you need RG, you need integer, floating points, all kinds of things that you store. And these are not images, they're assets that go into your engine. They might be normal map or displacement or color lookup tables or all kinds of things. And these formats for images, they're just for images. OpenEXR solves some of this, because at least you get floating point images. But again, OpenEXR is not really implementable. There's a subset called ACES, which is, but that standard is hard to come by. Okay, so we have this common problem. So let's look at HxA. HxA stores its information in a number of nodes. So a HxA file starts with a version number of the format, and then count a 32-bit integer count for all the nodes that you're going to store. And then after that comes all the nodes. So we're going to take a look at these nodes. There are three types of nodes. There are nodes with only metadata. There are nodes storing geometry, and there's nodes storing image data. Here comes the content of a node. So first you have the type of the node, which is just an uint that says what type. And then you get metadata. We're going to get back to metadata later on. And then you get either geometry or image data if it's a geometry or image node. If it's a meta node, then there's no geometry and no image. And inside of these, we have some information. We have a vertex count, an edge count, and something called a stack. And in our geometry nodes, the stacks are where we store the geometry. And if you look at the image, it also has a stack. So we're going to take a look at what that data actually is. So a stack is a number of layers. Each layer stores some information, and each layer has a number of components. So for instance, a layer might be an image with RGB for 3 components. This data is then stored as an array in either uint8, integer 32, float, or double precision. And this means that you can really easily access the information. So how do we build a piece of geometry? So if we, for instance, have 2 polygons like this, we would have one vertex layer that would be 4 vertices with 3 values per vertex. So those 3 values would be x, y, z, obviously. And here we have the vertex 0, vertex 1, vertex 2, and vertex 3. And then we need a corner layer, and that is our references that references which vertices are bound together in order to create geometry. And for that, we need 6 values with 1 value in each, right? So in this case, the values are 0, 1, -3, 2, 1, and -4. So why are there negative numbers? There are no negative vertices in this one. The vertices go from 0 and up, right? So what we do is we use negative number or the sign bit of the reference to say, this is the end of the primitive. So since this is 2 triangles, the third value is a negative value. So if you look at the first triangle, it references vertex 0, vertex 1, and vertex 2. The vertex 2, you can easily calculate it's -1 -2, so we get -3, and that gives us the number. This is a convention that FBX uses, and it's a very convenient way to store sort of the end of each primitive. If you want to add some data, like UV data, we can add another layer that says, for every corner, we want to store a value, actually 2 values, one U and one V, and then we can store all our values. We can add an edge layer. So now we have 6 edges, and we can store, for instance, creases. We can store even more data. We can store a face layer, which would be 2 values. And then, we might store, say, a polygon color or a material ID or something like that. On top of this, we have the metadata, and the metadata is really anything you want. So it is this structure, and it's essentially a simplified version of a JSON. So you have a name and then a data type and an array of that data type. And the data can be a 64-bit integer, it can be a 64-bit floating point number, it can be a node value. So that's a reference to a node. So for instance, if you store information that is like this node is, connected to another node, then you want to use a node value and not an integer, because if somebody changes the data, you want to know that, oh, this value actually means something, so I should transform. You can also store text, and you can also store binary data. And you can also store metadata inside of metadata, and that means that you can build a structure that is a tree structure where you can store arbitrary data. That's really it. That's all of the format. That's how simple this format is. And that's kind of the whole point. We want to create a format that you can implement in an hour or less. Anybody should be able to look at this and be like, oh, I can write that. And if you're doing something else, like you're trying to do your first, rendering engine, you don't want to write a really complicated reader. You want something super, super simple. So this is kind of the core value. It's less is more, make it implementable. So we have very few features, but it also means that everything kind of works because everybody can implement everything. But what about everything else you might want to do, right? You might want to store, all kinds of data. You might want to store animations or what have you, right? Maybe you want to store something super specific, yeah, like you want to store the temperature values on your surface or something like that. Well, for that, we have conventions, and anyone can add a convention. So if you have a very specific use case, you can say, I use HxA this way. I store this very particular data in this particular way, and you can publish that. And then if someone else is doing the same thing, they can say, oh, great, this is how you store X, Y, and Z. I'm going to store my stuff the same way, and now our stuff is compatible. So here is some of the soft conventions that are, already defined. So if you create image layers that, have distortion or displacement and ambient occlusion and all these common things that a lot of people will do, this is how you name your layers. And if you name your layers along these lines, other people will be able to build automated tools that say, oh, I know what this layer does. I know what this layer does. And you can automate things. Okay, great. But does the world really need yet another file format, right? There's a lot of file formats, and people have sort of suggested a lot of reasons why we should use their file format. And it reminds you of this comic strip of, you want a standard and you create yet another standard, and then you get more standards. So HxA is a little bit different because HxA is not meant to uh, be another thing you have to implement. It's actually meant to reduce the amount of code you need to write. So how does that work? Okay, let's give an example. Let's say you're writing an application and you want to load in a file, right? So you load in a HxA file. You write your own loader and you load it in, right? That's pretty straightforward. But HxA is a file format, but it's also an in-memory representation. So you saw the structure that I show you to show you how things are stored on disk. Well, those were typedefs that you can store in memory. So that gets really interesting. This turns out to be really, really important. So let's have a look at why. Let's look at your application. If you have a loader, that loader will load into memory in the HxA format in memory. Once it's in memory in your application, you can take that data and do whatever you want. Maybe you build a BSP tree or God knows what you do for your particular use case, right? The nice thing here is that if you use the internal HxA format, you can use an existing loader, right? So I've implemented a loader and you can use that, but you can also write your own. So if you have a different language or anything like that, it's always meant to be that you can implement your own. Okay, so what if the data doesn't do what you want, right? HxA can store n-gons. Maybe your rendering engine that you're writing only takes triangles. So you want to massage the data a little bit. Well, then you can use a utility, right? So I've written a utility that takes HxA files and it takes all the n-gons and splits them down into triangles and spits out a new HxA file. Great. So you can imagine in the future, you can download a bunch of various command line tools or similar that you can process your data. So now you can build a pipeline so that your application does what it needs, right? Okay. So what exists so far? There's a bunch of little utilities that I've written, like generating normals, triangulate, converting types. So for instance, you have float and you have double. Sometimes you only want one of those. So you can say, turn all the doubles into floats. You can split vertices for GPU work, which turns out to be important. You can close holes, which matters if you're doing volumetrics and things like that. There's a validation to make sure that the data is correct. And of course, there's UV unwrapping from Ministry of Flat. So all these things you sort of can use off the shelf. And you can use this to build your own pipeline. Great. But let's have a look at what's inside of these utilities. So if we look inside of one of these utilities, they have to load a HxA file. They store that HxA in memory, and then they do something, and then they get a new structure of HxA in memory, and then it saves that out, right? That means that inside of this utility, there's actually a function that looks something like this that takes a node and triangulates it, right? So the really cool thing is that you can take this function, if it's open source, and you can put it inside your application. So since you're HxA loading, you are now running this utility for all the data comes in. And now you don't need your pipeline anymore. You can now move this code from outside your application to inside your application. Right? But what if your data isn't in HxA, right? The world doesn't use HxA yet. So I still want to use this, right? So of course, I can use a file converter, right? I can load in a file, it turns it into HxA in memory, and then you use the HxA saver to save it out. And then you use your loader and load it into your application, and then you can run the utilities and all that stuff. And now you have a system where somebody else had to write the hard file converter, and you only write the very simple loader file. But wait a minute. Once you've done this, you can actually take that file converter and just put it into your application. You can just drop it in because it turns the file that is of some hard to parse format into HxA memory uh, representation that your application already reads. And that means that if someone writes a new file importer, you can just drop that into your application code and say, now I also load in file X that I couldn't load before. And that allows HxA to sort of be an intermediary format that the end user may not even see, but that can really help you develop your application. So already now there are some implementation. There's a PNG loader and saver. There's Targa. There's an OpenEXR that is under development. There's an FBX loader, which actually uses some of the work that the Blender Foundation has done to reverse engineer FBX. So it does not use the Autodesk FBX. And there's also a true type loader. And that means you can take any font and load them in as geometry, because anyone who's ever written an engine knows that it's usually the hardest thing to do to get your engine up and running is to do the performance counter, because you need to write like text in the corner to get your FPS, and writing text in 3D is really hard. But that's solved here because you could just load in any true type font and get polygonized types for um, any language you want. All of these are written in C. They have zero dependencies, and I'm constantly writing more stuff. Okay, so this means you have sort of drop-in open source, right? Anyone can write a little plugin, and you can drop that into your code, and just it operates on this common data format in memory and does really neat stuff, right? That's super useful. And it's really about fostering open source and interoperability. And I think we can make it even better. So hold on. This function that we talked about before that takes a piece of HxA structure and it does something to it and returns a HxA structure. What if we could load that dynamically, right? And that brings me to the HxA Universal Plugin Interface. So what is that? Well, it means you can dynamically load code that operate on HxA data structures. Okay, let's have a look at this. So what you do is you implement a plugin and you say, here is my function that operates on HxA, and you fill out this sort of form and say, here's the parameters that I use, here's the name of my plugin, here's the description of my plugin, it outputs HxA this way, and so on and so forth. And then you use this function at the bottom to load this library and initialize your function. So you're basically telling the system, here's my functionality. Now you can compile your code as a DLL or dynamically loaded library, and any application that supports this can now load in this plugin dynamically and access the code. The parameters for this is this structure, which starts with a type. So it has a type and it says, what are you storing? And then a name and a description. And then you can store a Boolean or, floating points or vectors and texts and things like this. And that means that you can control exactly what your application does and create an interface for it. So if somebody makes a plugin into an existing application, they can make a UI for this plugin that is, native to that application. Okay, so this opens up a huge amount of really cool opportunities for the industry, right? You can have one plugin that you can run in multiple DCC app tools. That's really powerful. It can be integrated with a native UI. It can be scriptable. It can run in the cloud, right? You can make some kind of service where you can run these plugins and configure them and sort of have a cloud operation where you build a pipeline of processing things. You can build huge amount of rich custom tools. So you can say it's really easy to make a custom tool that isn't tied to specific tool environment, and that's incredibly nice. Another thing is that since we have loaders that load into HxA, we now have universal loaders and savers. And that means that any application that can load in a file using the plugin interface can now take a new saver and loader. And that means that if if you're using an application that supports this, and somebody comes up with a new graphics format or something custom, you can just get that plugin, drop it into the plugin directory, and boom, now your application supports this new format. And that means that it's much easier for people to create custom formats. So a good example of why you might want to do that is a lot of game engines and things like that. They need very specialized formats for their engines to work. So now you can make an exporter for that and it just works. And of course, this all integrates into existing code. So you don't have to rewrite stuff. So HxA is not a monolithic project. It's not supposed to be, a huge project you download and, you have to get it to build on your platform or anything like that. It's just a tiny bit of agreement. Like if we all agree to use this sort of convention, we can make things work really well together. So what is missing from HxA, right? So more components, obviously. The more components we build, the more valuable it gets. For me, it's already valuable because I have a bunch of components and they're available. I'm constantly making more. But the more people that are contributing components, the better it gets. Obviously, we're going to get more domain specific conventions so that it's more useful for very sort of niche areas. A community would be super nice if we can get some. Application integration would obviously be really nice. I'm hoping to get some plugins that actually expose the plugin interface. So it'll be a plugin within a plugin for some DCCs. That'd be really cool. And of course, more sample code and documentation. Right now, most of the documentation is actually in the HxA.h file that has the data structure, but also a description of how everything works. What HxA does not need is broad industry support to be useful. Sure, it's nice, but the whole point is that everything should be useful even if the whole world doesn't accept it as a standard. So that's really my presentation, and thank you very much for listening. If you want to get in touch, I am at this. Here's the GitHub, and you can also email me, and you can also find me on Twitter. That's it. Have a nice day.